So we are at the last step of this 4-lecture course, and so the idea is to use this occasion to work out how the M2S sequences works, and these are sequences that convert magnetization into singlet state and vice versa. In the case of nearly equivalent spins, so in the condition in which the difference in the chemical shift is much smaller than the J gamma. Okay, so for this case, so the sequences are built upon blocks, and this block is made by a spin echo, so which is quite current recursive motive and pulse sequences in general. And so you have a pi pulse, 180-degree pulse, in the middle of symmetric delay, that's we call tau. And in this particular application, this time tau is synchronized with the J coupling. Okay, so somehow we are going to define that in due course. So the first thing is to study what happened during one of these echoes. What happened in particular in the singlet and triplet space. So now, if you remember, we have wrote before we've written the Hamiltonian for this system, and the Hamiltonian, if we choose a base which is alpha alpha, if we choose the singlet and triplet base, of course, so we T1, T0, S0, and T minus 1. So it's just a convenient way to organize that. When we look at the Hamiltonian in that base, we have found that we have something down here. We have a 2 by 2 which connects these two states, and then we have something else down here, and then everything else is 0. Okay? So one wonders in this situation, is a 2 by 2 is nothing else than similar to what happened for a single isolated spin a half, where you have only 2 energy levels. So one wonders if one can use a similar approach and get the benefit of that approach in a more complicated description. So in principle, what I would like to do is basically isolate this thing and try to work out only in this block by defining operators which behaves like the spin a half operator. So like Ix, Iy, Iz, and the identity for just a single spin particle, spin a half. Okay, and this can be possible. And in fact, the technique is called fictitious spin a half operators, because they basically are fictitious, because then the system is not really made by a single spin a half, but we can use them in this context. Okay, so this can be, so essentially, if you have like two spin states, you can define Ix for state 1 and 2 in terms of a half, and then you have to use take the difference, or the sum, sorry, to 1. Okay, so basically you take the ket for one of the states, multiply it by the bra of the other state, and so on. And now you can define Iy for the same pair of spin, which is 1 over 2i, and then here you take the difference. Again, you can define the z as a half of 1, 1, minus 2, 2, and the identity, which is 1, 1 plus 2, 2. Okay? So why I want to do that is because this, so if you forget for a moment this label stuff there, the 1, 2 there, These are the normal spin operators we have for a single spin, and the commutation rules are actually preserved. So if you take one of those, so x and y, for example, for some spin pair, let's call it alpha and beta, or yeah, whatever. Okay, so this is basically they commute if alpha is different from beta, and they do not commute, and they give the usual commutation rule if alpha is equal to beta. Okay, so if we have ix alpha, say iy alpha, then we have the usual cyclic commutation rule. Okay, and then we can use basically this in the following. Okay, so as you see in equation 2.5, we have the matrix representation of those states. Clearly, you can define the same for the other couple, the triplets there, and then you can look how they look in terms of matrix representation. So the next task would be to write the Hamiltonian using now this set of spin operator rather than the spin operator rather than the product operator that you would normally use in the case of two spin system. Okay, and so in the test here is very detailed, and I follow what happened in the singlet and triplet manifold, so in this subspace, but I also follow what happened in the other one. And I think on the board, just to simplify, we can just follow what is really neat. So just follow what happened in this subspace. But you know, it is everything is completed on the paper here. So what we want to do next task is basically the Hamiltonian. It's as usual. We have written that many times. Is the difference in chemical shift IZ I1Z. Minus I2Z. Then we have the sum of the chemical shift, I1Z plus I2Z. And then we have the J gap, I1 dot I2. Okay, so now these are like operating in the whole space. We would like to transform that into this. And this can be done by rewriting that as a sum of term. So a term which is actually living only in the singlet 0, triplet 0 subspace, which is this one here, and one which is basically living in the rest of the space, T1, T minus 1. And as I said, we are going to restrict our attention on the board at least to this term here. And this can be written in terms of delta omega Ix S0 T0 plus omega J Iz S0 T0. Then we have a term which involves the unity operator. And then we have an analogous expression for that term as well. Now for the time again on the board, so this term doesn't bother us too much because the unity will come with everything. It doesn't generate evolution or anything, so we can just, it will add a phase at the end, but we can just forget about that. Again, in the end notes there, basically it is carried through. But at the moment I will concentrate to the main, more important part, which actually generates the evolution in the singlet and triplet subspace. And the way we can use the same trick that we used last week, noticing that these operators can be seen in a space or in a block sphere, if you want, made by this single transition operators. As we would do for normal Ix, Iy, and Z. Okay, and what this Hamiltonian says, he says that there is a component down here whose intensity is delta omega, And then there is a component up here, which is, this component is actually, the strength is omega j. So they may be seen as a field pointing at some angle from the z. And then this whole thing can be seen as a rotation around y of this angle theta, by this angle theta, of Iz S0 T0, multiplied by the strength of that, which we call omega E. And as usual, omega E is nothing else than the square of omega j plus the square of delta omega. And theta is defined such that the arctan of delta omega divided by omega j. Did I miss something? No? Okay. Okay, so now this trick allows me to write the Hamiltonian and this subspace as simply omega e rotation superoperator, that is a superoperator, by an angle theta multiplied by Iz S0 T0. Why I would like to do that, so I make some more space first. It's because so once I have that, I can essentially calculate a propagator. So this Hamiltonian, applied for a time tau, will give me an exponential of I tau h. And so if we restrict our rotation to the S0 T0 there, this will be e to the minus I tau omega e ry theta Iz S0 T0. But now you know this trick that if we have an exponential of a rotational superoperator, you can demonstrate that it actually, you can take the rotation superoperator down here. Okay, I would actually label that S0 T0 as well, to make sure that we know that we are in that subspace also for the rotation. Okay, and this becomes a rotation. Whatever, if I take this out, what is left there, it's a rotation around z of an angular quantity made by omega e tau, and this is that. Now, since this is an operator as well, a superoperator as well, we will have to rotate on both sides. Okay, so the propagator is made by these three rotations in the subspace made by S0 T0. Okay, next things we need. So now we know how to write the Hamiltonian during these bits here. Okay? Or the propagation during these bits there. Now we need to understand what the pi pulse does. And to do that, we use this simple approach. So if I take, so pi pulse is nothing else than a rotation around x by an angle pi. If I write down the matrix representation of that, I found out that this is written like that. Okay, and 0 elsewhere. Okay, this is not in the subspace yet. So what I see here is that, remember how I organized my base, T1, T0, S0, T minus 1. So what this says is that a pi rotation or a pi pulse doesn't do anything on my single state, stays where it is and with the same sign. It changes the sign of the T0 and it changes the sign but also inverts the position of T1 and T minus 1. Okay? So now again, by inspection actually, you could demonstrate that this can be written in the subspace as the product of a rotation around z in the S0 T0 space, and then a rotation around x of pi in the T1 T minus 1. And you can do that by inspection. Basically try to use the IZ and the IZ S0 T0 and IX T1 T minus 1. Take the matrix exponent of that to make the rotational superoperator and then match with that. Okay? So now we have another piece of the puzzle. Again, I will restrict my attention, at least on the board, to this bit here, which is what happened to the singlet in that subspace. Just a note, I can do that all the time because basically, as I said before, these two subspaces commute, so I can just take one of them because I can always separate everything in T1, T minus 1 on one side and T0, T0 on the other side and work them independently just because they commute because belongs to different subspaces. Okay, so now I'm in a position to write the the propagator for the echo, which of course lasts 2 tau in this subspace only. And this is made by minus I, which comes from here. And then we have the propagator during tau, which is written here. Ry theta z omega e tau Ry minus theta. Then we insert here because we have done that. Now we do this. So a pi rotation in the middle in the same subspace. And then again the evolution, which is just copying this on this side. And this is basically the full propagator, which works in that subspace during one single echo. Okay? Now, what's the first things we do here? We notice that if we want to be like J synchronized, so we will define our theta, our tau, as pi over 2 omega e. Now if we look at the equation for omega e, in the limit that this is very small compared to that, clearly this approximates with omega j. So if you want, this is also nearly equivalent to pi or pi half over omega j. Okay, and this gives you the idea. So this contains the j. That's why it's essentially. Actually, this is, you can actually go a little bit further. So this is like 2 times 2 pi j, and this goes, and this is basically nearly. This is 1 over 4j. Okay, so the synchronization is that the echo delay is a quarter, 1 over 4 times the j coupling. Okay, so if we do that and we substitute this equation, the first equation in there, those became rotation of pi half. Okay, so that makes my echo j synchronized. And now the next task takes a bit of time. It took me a while also to understand how to proceed. But we could demonstrate that these things here, it's nothing else than a rotation around x in the same subspace by an angle made by 2 theta. Okay? So this is written in the appendix, and I wonder if there is time to go through, or we could probably do. Can we do it? Okay. maybe we can start showing how this is done basically. So one takes here a little bit of an inner piece. This is what is called usually a sandwich, a rotation sandwich. And if we look at that, what we do, it's again a common trick. It's to insert here some extra rotation. So if I insert here a rotation around Z by minus pi in the same subspace, and then I insert that again. Okay, I'm not doing anything strange because this is back to 1. Okay, but then I can isolate this bit here. And this is what? This is essentially a rotation of y around Z by an angle pi. So it changes the axis. Right? So if you remember, so basically what we are doing, we have to rotate around Z, something which is along y, so it goes to minus x. So this is the same like r minus x theta, okay, but this is also the same like rx of minus theta, right? Because either you change the axis or the sign of the angle you are rotating, okay? So either you rotate it like that, or you rotate on this side but with the opposite angle. Okay? Remember that now we have this to carry with us. Okay, now you see here, you have one rotation here and one rotation here. They are both rotation around the same axis of the same quantity. This becomes ry minus 2 theta. Because you basically rotate twice in the same direction. And then we have this to carry. Now we have solved all these bits here. And now we can try to get to the next level. So we get this here and that on this side. Okay, so remember, now we can add a rotation of pi half and then a rotation around Z of pi half. So this comes from here. Okay, how I solve that? So my problem is that if I would like to rotate that, I will have to have a rotation of pi half on one side and a rotation of minus pi half on the other side. Okay, because that's how rotation works. So the trick here is to add again two rotation around Z, this time of 2 pi. I think I have to use minus 2 pi first. Yes, minus 2 pi there, and then 2 pi. Again, I'm not adding in practice anything. But now you can see here, these are all rotation around pi, which sum up, and the sum of that is a rotation of minus 2 pi, which is what I want. Because now I can take this term, and this term, and this is what? It's a rotation around Z of pi half of y. So again, I have y, and I rotate it again back there, and it becomes r minus x of minus 2 theta. And I use the same trick as before. I change the sign here and I change the sign here. So this is exactly a rotation of x around x of 2 pi, of 2 theta. Okay? And then I have left with this. But what is this? A rotation around z of 2 pi is nothing else than minus 1, minus unity. So this simplifies to minus 1. And I have to bring now down those two last terms. So I'm left with r y theta, r x 2 theta, and now r y minus theta, all in the same subspace. I have a minus to carry here, so I'm left only with I, and that's my final thing. And now here one makes the approximation. So if theta is smaller than 1, which it is usually because theta is coming from here and the omega j is bigger than the difference in chemical shift. Therefore, this is a small number. In this, you can basically now demonstrate that actually this approximation is just a rotation around x of 2 theta. Okay? So for small flip angles, this notation here is nothing else than that. And to demonstrate that is also quite simple, because you have to use the expansion for the exponential we have in here. Okay? So, for example, the expansion here will tell you is the expansion here is like unity minus I theta iy plus other terms, which I neglect. The expansion here is unity minus I theta 2 theta iy plus other terms which I neglect, and then here we have 1 plus I theta iy and other term which I neglect. Again, one can take all the multiplicants here, all the multiplication in there, and keep only the one which depends on the first order in theta. Neglect all the higher order. And in there you are left with 1 minus I 2 theta iy plus higher order terms in theta. Okay? And this is nothing else than the exponential of a rotation about this is x, sorry. Okay, about x of 2 theta. And we have demonstrated this equality. Okay, so just expand the Taylor series of the exponential, multiply, take only the first order term in theta. That's the approximation which you can do it because you're supposed this is much small number, and then recompact the series into an exponential. And now you have demonstrated that. So, after all this, we have shown that all this big B here can go, and we are left only with a rotation around x in that subspace by 2 theta. So the next thing is, if I now make sure that I take 2 theta n equal pi, therefore I choose n as pi over 2 theta, this becomes a rotation of 2 pi. So if I take this and I replicate it n times with n satisfying that, this is a rotation around x of pi. Okay? So now here we have to go back. So back to the sphere. To the block sphere. So unfortunately this doesn't work out. So in the block sphere we have, so any point in the block sphere can be so basically any point in the block sphere, it's a representation of a two-spin system, a two-level system, sorry, and essentially you get a function which, if you have this angle, let's call it something else, phi, and then you have theta and phi. represent points which belongs to the two energy levels you have there. And what we have shown is that if I do that with tau J synchronized and n done by that, I can realize a rotation around the x-axis by pi, so I can take the triple state down there into a singlet state. So this strain of echo, done with these numbers, inverts, so changes singlet state into triple state and vice versa. Okay? If I take half the number of echo, which is what we're going to do a bit later, I can basically generate coherences between the triplet and the singlet, because I just stopped halfway here, okay, on the x and y plane. So coherences between the two states. Okay, so now with these things in n, we can describe the whole pulse sequence. And the space as well. So an M2S pulse sequence, the acronym is clearly, we go from magnetization into singlet, starts with a 90-degree pulse, and then is followed by one of these J-synchronized echo train. We do that n1 time, which work with n1 equal to pi over what was it? 2 theta. And then we do another 90. At the end of that, we do another 90. We leave a delay tau, and then we do another set, another another echo train with n2, and n2 is n1 halves. Okay? So what I'm saying is that if we feed that with longitudinal magnetization, we can on this side and we get some singlet order. This generates, in fact it generates a difference in population between these levels. Okay? And IZ is nothing else than a difference in population between the outer triplet states, right? So okay? So we do that using these tools. So let's see. We start from equation 7.1. So we start with IZ, and then as I said there, IZ is nothing else than T1 minus T minus 1 plus T minus 1. Okay. So again here I normalize that thing in order then to get the proper efficiency. And the first thing we do is a 90-degree around Y. Okay, and this generates coherences between the triplet, the outer triplet. So let's try to follow it. So when we start here, if we look at our energy levels, we have a difference in population between the two outer triplet states, which is IZ. Okay? After that pulse, here, we generate coherences between these two outer, between the outer triplets and the central triplet. Okay, so if we do that, this became square root of 2, actually this became 2, and then we have t1 plus t minus 1, which multiplies t0, and then we have t0, which multiplies t1 plus t minus 1. Okay? So these are coherences between t1 and t0. One of those. Now we apply this echo train, and we have seen that this echo train is nothing else than a rotation in the S0 T0 pi pi. Okay, and this basically changes singlet into triplet and vice versa. So basically this will be exchanged now with singlet. And then there is I actually that is in front of everything, if you remember in there. So this becomes T1 plus T minus 1. The triplet there is exchanged, it became now a singlet. And then we have okay, and now we do a 90 degree around X, and the effect of that, you cannot do anything on the singlet because singlet states are not magnetic, they are not affected by pulses, but it does change the triplets into T0 terms. So what, according to equation 7.3, so if we now do the 90x, what we get is that this bit here becomes T0, and we are left with 1 over square root of 2 T0 S0 plus S0 T0. And now we can actually call back the fictitious spin operator we defined before, and noticing that this is equivalent to square root of 2 times Ix S0 T0. If you remember, or you can check actually in the equation at the beginning, the way we define in equation 2.2, the way we define Ix, the fictitious Ix for this two spin level system. Okay, so we are at this stage here. And this is now what? This is a coherence between T0 and S0. Okay, so at this point here, we have now changed that into coherences between T0 and S0. Okay? Now, next thing is to do tau. So now we evolve for a time under the Hamiltonian U, under the propagator U of tau, which is given before. And if you look at it, it is actually a rotation in the limit of small theta. It's a rotation around Z of pi half. I think so. Okay, so rotation of pi half around Z will bring this again my small z-axis plot, x, y, and z. We have ix, so we have something down here. We rotate around z by half, so we are changing that into iy plus. Okay. And finally, we do an echo, which lasts half of what it lasted before. So instead of applying a rotation of pi, we apply a rotation around x of pi half in that subspace. Rotation around x, so we start with y, now we are here, and we rotate around x by pi half, and we go back to iz. Square root of 2 iz s0 t0. Okay, but what is iz s0 t0? If we go back and look at the definition at the beginning, this is given in equation 2.2 again, and this is basically proportional to t0 minus s0 s0, which is a difference in population now between the triplet and the singlet. So at the end here, we have generated a difference in population between this level and this level, which is what is long-lived and which is what we want. Okay, so just a few more, just another thing before to go. And is when we do this transformation, we would like to know how much of the singlet of basically iz that we can convert into singlet and vice versa, which is very important because if you do an experiment, and the sequence works, but then you lose you lose part of the population you have at the beginning. This is a waste, of course. So the next section 8 here, demonstrates that actually this is not the case. First of all, you demonstrate that the transformation between iz and these terms here is 100% efficient if you use a unitary transformation. Okay, so back in the days, Malcolm and Sorensen, they were working together, I think, in Amsterdam, something like that. They figured out, so there are a couple of papers, they figured out that if you use only to restrict to unitary transformation, which is what you want to do because you want to preserve the norm, the maximum transformation when you go from A to B, so if you want to transform the operator A into operator B, which now we want to transform iz into this operator here, it's given by lambda b dot lambda a divided by lambda b, where these lambdas are the eigen values of the operators you have here. So you have the operator, you represent in the basis, and you take the eigen values of that. And then you multiply together, take this division here, and then you get the maximum transformation. So in our case, we would like to go from iz, in particular we want to go from 1 over square root of iz, which is the normalized value of that. You do have to normalize if you want to get the right percentage there. And you end up into this, so square root of 2 iz s0 t0. Okay. So that's the starting point, that's the end point. If you do that, equation 8.3 gives you the lambdas for these two operators, and when you do the equations here, you find out 1. So this is 100% efficient. Okay? Now, this may sound a bit strange, because when we talk about this transformation, we often say that we actually do the transformation, but we have to pay a price, because we lose part of the starting magnetic polarization. Okay? Why is that? The problem is that as soon you have that, M2S does that, and does that 100% efficient. Okay? On the paper. Okay? In theory. Clearly, during the sequence, experimentally, you may have all sorts of complications. Your passes are not perfect, you have delays, you have T2 during these delays, and so on. So the experimental efficiency may be lower than that. But at least we know that in principle we can do it with maximum efficiency. The point is that this, you create that, but we know, we have seen that in two lectures ago, that if you have this picture and you create a difference in population between that and that, I used now 3 posts just to simplify what I want to say, these levels are interconnected, and this is the singlet transition, let's say it's weak, okay, which is because this is dominated by TS and this is dominated by T1. Okay, we know that our TS is much longer than T1. So when we do our experiment, for example, we wait for a time longer than T1, but shorter than TS. So this has time to re-equilibrate, while most of the population stays in the difference between the singlet and the mean population of the triplet. So this, when you use a time which is bigger than T1 but is smaller than TS, goes into singlet population minus the average of the triplet, which is the sum over m of Tm. Okay? And now the thing changes, because now this final operator has a different value for that gamma, and what works out is that when you do this equation for that operator, you find square root of 2/3. So the efficiency is not 1, it's something like, I think it's 0.81 or something, roughly this value here. Okay? Often in our experiment, we create singlet, we wait some time, and then we convert back into magnetization by turning this path sequence into an S2M. So just reverse in time, run it, go back to magnetization. We lose again a factor of 2/3. Okay? So if we multiply that by another factor of 2/3, you get 2/3. So this is the efficiency of going back and forth from IZ into singlet and back into IZ, considering that we basically re-equilibrate the triplet in the meantime, and in fact often we choose to kill everything else, right, by applying a singlet filter. And when we do that, we are exactly doing that. We are basically taking just a part of that. Okay, and you will end up with this equation again. So you kill everything else is not singlet. So you kill the magnetization. Essentially, you equilibrate that, and then you are back at this point. So experimentally, we have always to confront that the best we can do theoretically is 2/3, going back and forth. And in practice, we always notice something less than that, because we have all sorts of experimental problem in